Thank you for joining today's WebGL and WebGPU Meetup. Joining us today are Ken Russell from Google, Kelsey Gilbert from Mozilla, Aaron Oliker from BioDigital, Oleksandr Popov from Intellias, Kari Lavikka from the University of Helsinki, and Alexander Rose, Independent. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll share the link to the recording along with the slides on the event's webpage. At the end of the session, please complete the short survey form to help us better design future events. On today's agenda, Ken Russell and Kelsey Gilbert will give us updates on the latest from WebGL and WebGPU working groups. Following the updates, Aaron Oliker will debut BioDigital's new WebGL engine. Oleksandr Popov will demonstrate the rendering of a stylized castle. Kari Lavikka will demonstrate GenomeSpy, a GPU-powered visualization grammar for genomic data. And finally, Alexander Rose will present on scaling up molecular graphics library using Molstar. Now let's start the meetup with Ken Russell, chair of the Khronos' WebGL working group. Ken?
Okay, how are we looking? Can you see some slides?
Looks great.
Okay, super. Let's dive right in. Okay, so we've got a brief agenda, but we really want to get to the meat of the presentation. So let's, again, just dive right in. So first, I encourage everybody on the call to please join the WebGL and WebGPU communities. We got some vibrant online places for you to join and tell us all about your projects and ask questions about how to do various graphics techniques. So, please peruse these slides later, but we have a WebGL developers list as well as the public WebGL specification list over at Khronos. And we've got a matrix chat room where you can, in real time, talk to the browser implementers and tell us where all the bugs are. The WebGPU contact information is discussed later in the presentation to deduplicate some information. Okay, so generally speaking, what have we been doing over the past couple of months? We're continuing to maintain and enhance WebGL implementations. We've done some smaller fixes to the conformance suite and some draft extensions. There are several smaller WebGL extensions on the way toward community approval. We'll talk about that. There's some progress on the Pixel local storage extension, and there have been performance correctness and security fixes for various partners. So some progress on the smaller extensions. During the last meetup, several smaller WebGL extensions were discussed for inclusion, and these have all been implemented and conformance tests have been written, largely thanks to Alexei Knyazov, who is associated with Khronos. So right now, 5 of these have been community approved: clip call distance, X clip control, depth clamp, polygon offset clamp, and polygon mode with some caveats because that one's really non-portable. And we will continue discussing the others. And these enable various, performance and correctness improvements to certain algorithms like shadow mapping, for example. And also, actually, one of these, the clip control, makes it possible to make WebGL and WebGPU content render the same with the same coordinate systems. So it's a really handy bridge API and extension for getting your content ready for WebGPU. So this is the full list. We're aiming to basically community prove all of these, and they're on their way. So a little update on Pixel local storage. As has been discussed during the last meetup, Chris Dalton from Rive is developing a Pixel local storage extension. This lets you do programmable blending. It's really cool. It subsumes blend equation advanced coherent and is actually more general than it, and has been demonstrated to give you like 10 to 100 times speedups depending on your hardware that you're on and the kind of graphics algorithm that you're trying to implement. The draft implementation is already available in Chrome Canary. Just go turn it on WebGL draft extensions and you can test this out and build your application and get it working. And we would definitely encourage you to do this. There's a demo checked into Khronos' WebGL repo that shows how to re-implement all of the advanced blend modes. And this is going to ship as soon as we finish the last couple of driver bug workarounds. I think we have one on Mac AMD and one remaining one on Qualcomm. So this is really getting ready to go, and we would encourage you to try it out now. Please try it and provide your feedback. Thank you. Okay, so a little progress on Angle's metal backend. This is an area of active work, and as mentioned before, is used by WebKit's WebGL implementation on Mac and iOS. Some major recent changes have been fixes for crashes that were seen in the field as it's been launching in Chromium. some correctness fixes to uniform buffer caches and PVRTC uploads from pixel buffer objects. There have been optimizations to the handling of provoking vertex format conversion, implicit MSAA resolves on Apple Silicon, and emulated texture formats like Luminance and Alpha, which, fun fact, are used by Zoom. And we're slow on the metal backends until we optimize them. So thank you to Jeff Lang, Kuyen Le, who's the original author of Engel's metal backend, Kyle Piddington, who is like one of the major rewriters of Engel's metal backend from Apple, and Alexei Kniazev for these. The correctness and performance of this right now are generally better than OpenGL, and we're continuing to diagnose customer issues, but this is intended to ship in Chrome 119, which is going to stable right now. So let us know if you see any issues right away, but we think that this is ready to go and will actually improve the situation for customers. And now let me hand it off to Kelsey Gilbert to talk about WebGPU.
I'm now unmuted. Hey all, Kelsey here. I'm here to talk about WebGPU. I'm one of the two co-chairs of WebGPU with Corentin Wallace and at Google. I'm at Mozilla. And here's our update. WebGPU, y'all are pretty familiar with it at this point. We are working on continuing to get it out the door. If you were here for our July presentation, some of these slides may look mostly familiar. And that's because we've been doing a lot of implementation work, primarily. Spec work is still ongoing, but let's get into it. Next slide. The main standardization updates are that we are increasingly at a 1.1, like a 1.0, sorry, kind of level. Nothing has gone to like full published yet, but we are getting there. We are still talking about the major discussion point right now is compatibility mode, which is how we can help deliver WebGPU to machines that don't have drivers which support our original matrix of like APIs that we're supporting. So originally WebGPU is going to be kind of a like D3D12 Vulkan metal implementation, and now we're looking back in time to see if what we can offer for people who are still on hardware that's D3D11 and OpenGL ES, especially on Android and older Windows. We have a lot of consensus here, but there's a lot of little things to figure out. So expect exciting news there. Other features that are very exciting is FB16 or shader F16 is specified and tested and shipping in Chromium. So super exciting there. Work in Firefox is coming, but not ready yet. We also have smaller features like read-only and write-only and read-write storage textures. These are requested by external partners. We are very interested if people have use cases that they can't quite satisfy with WebGPU, like talk to us. This is an example where someone came to us and said, like, we would really like this thing. And here we are, like trying to figure it out and trying to help them deliver. Implementations are at varying stages of completeness, but it's getting better every day, week by week. Try it out. It mostly works. Like we expect it to work. Chrome does just work. Firefox is most of the way there. And if you've run into new bugs, report them to us. We're expecting it to work. Next slide. Implementation status. Sorry, I got ahead of myself. Here's our implementation status. In Firefox, we're enabled on nightly in Windows and Linux, still working on getting Mac up and running, but we are expecting to ship to release by end of year. Our main to-dos are still indirect draw calls and some bind group compatibility duplication work, which is almost done, constant override expressions, which is almost done, abstract WebGL WGL types, which are in progress. Chromium is shipping on Windows, Chrome OS, and Mac, but not Linux. But here's the exciting news. It's out on Canary on Android. So that's incredibly exciting. So we're seeing real WebGPU on a whole bunch of mobile devices now, which is super thrilling. Check it out. If you find any issues, you know where to find us. Next. As I touched on before, we have a bunch of partnerships and collaboration that we do. We are not designing this like just in a back room by ourselves. We do a lot of discussions there, but like we really, really, really want feedback and want participation and want to know what people need. Because ultimately, like we're trying to build this for y'all. And if we don't know what you need, we won't be able to give you everything you want. So these are examples where we're working with existing projects, trying to make sure that they can deliver everything they want to and deliver it faster and better and nicer than ever before. Next. We have resources. This slide hasn't changed if you saw it previously. We still love these. They still apply. The actual state of the spec hasn't changed all that much in the last 4 months. So like these are still great tutorials. Check them out. The samples are great. They've been brought into the main the main repos now. So these are like the official samples, and you can check them out live. Next. Contributing. I mentioned it before. I'll say it again. Try it out. Just try it. If you run into issues, you're not supposed to. There's not supposed to be issues. We're at the point where we expect there to be some issues still, but we want to know what they are because we probably haven't seen them yet. So if you find issues, please report bugs. Please come chat with us. We have a matrix chat that you can come and just talk to us live on. We have various bug trackers, the whole 9 yards. The other things that are very useful is trying to contribute samples and demos and also helping with conformance testing. Conformance testing isn't exactly glamorous, but it's one of the backbones that helps us continue to deliver what's effectively these graphics drivers without regressions. Next. And that's it for me.
Hello, this is Aaron Oliker. Can you hear me? Can you see me?
Yes, good to go.
Okay, great. I'm Aaron Oliker. I'm Chief Innovation Officer at BioDigital, and today we're going to be presenting our new engine, Plasma, for our human body visualization platform, which is a WebGL-based platform. And you may ask yourself, what is a human body visualization platform? Well, it's, the very short description we call it, kind of like a Google Earth for the human body. And we have our system for web, mobile, iOS SDKs, Android SDKs, and XR. And all of that is using the same web view in most cases. We've been around for a while in different iterations. BioDigital last year powered over 100 million health conversations using our WebGL widgets. Over 4 million students, teachers, clinicians, and professionals use our system. A lot of big names out there, big schools, Medtronic, Google, J&J, all use our systems to communicate health concepts for education, for point of care, lots of different use cases, and we'll go through a couple of them. So why did we use WebGL? We started out a long time ago, like almost 20 years ago, and we were using, C++ executables. And when WebGL came out in 2011, we jumped all over it. We didn't have to deal with all the different problems that you had with drivers. Everything's in the browsers. It was very experimental at the time, so we took a risk, and we're one of the older systems that use it. But for health concepts, it's very hands-on. It's very engaging. You understand spatial relationships, very abstract concepts better using interactive 3D. And this has been proven in lots of different studies over and over again. So we do have the world's largest library of human anatomy, disease states, and conditions, all 3D models. And it's been reviewed many times by multiple medical institutions and whatnot. And again, our platform is, it's web-based. We have mobile, iOS, and Android. We have, I'll switch here to, we have a developer SDK and API for web and mobile. And, you know, our original engine was released in 2012. We released it, I think, one day after Google released the Google body, and then we released ours the next day or a week after, I can't remember, but it was like one of the big WebGL releases. Our old engine was a Scene.js based engine. I don't know if anybody remembers Scene.js, but it was abandoned and forked a couple of years ago. Our system was heavily optimized, but not very flexible, kind of tough to understand, a lot of old coding conventions, old hardware and software support assumptions. And so we really needed to upgrade our engine several years ago, and we knew that, and it was painful because we had so many implementations and so many clients out there using it, and we finally released it very recently. It says Q3, but probably Q2, end of Q2 of this year. And I'll show you our engine right now. So here you can see we're looking at the complete male anatomy. You're looking at, I think, about 8,000 different structures. And if I can go in close, rotate around, and just move through it, you'll see it's not just these external models, but we're rendering everything here, and it's very fast. And you get that's through the entire body, 8,000 different structures. Each structure has about 3 different references. So you have about 24,000 references for the entire body. And it's not just static, it's also dynamic. We want to tell health stories. And so we've really gone a long way to create these WebGL authoring tools as well. So you can, you know, you can learn about the electrical conduction system of the heart, how the heart moves and beats, you know, how it breaks down. And so you can go from like this normal, or this is not normal, this is atrial fibrillation to a normal heartbeat. And we have a this massive library of content. You can, if you want to go online and explore, you can. Almost every single, you know, all the anatomy, disease states, conditions are all here. So we, not only is it just like an app, but it gets integrated in all these different applications, and we have all these very broad network conditions that we had to deal with, and lots of texts that people author as they use our system. So the Plasma engine has a lot of different improvements from our old engine, improvements in the architecture, upgrades, lots of fixes. It needed to match or exceed performance because a lot of people are using it. And when we swapped out our old engine for the new engine, it had to be a smooth transition. Nobody could be down because they use it in these very important ways. And so we had to support their old WebGL 1 devices. And we also wanted to have that WebXR support. There are a lot of unique challenges for our new WebGL system. And I just want to note, Brian Trills is our chief engineer for this WebGL engine, not me. So we had a lot of unique challenges, lots of objects. Almost nothing is repeated. Nothing is far away. Everything is visible, as you saw with that full body example that I showed you. We have a custom pipeline. So we've always used Maya, and so you know, we have a custom exporter. We compress textures on the server. The authoring is done in app, and I'll you know, we have 2 different authoring platforms, one that's external and one that's internal, so that people can use all the different modules, all the different parts of the body to create their own stories, and various custom particle systems to show blood flow and things of that nature. And then we have some great use cases I want to very quickly take you through of just how our system's being used in the wild. One is actually the American Cancer Society, and this is their live site. And here you can see we have all the different explanations of cancer that's directly integrated as a widget into their site. Another is LCAST, which is the Lurie's Children's Hospital's child abuse plausibility tool, which is crazy. This was released this year. Here you can see Mary Clyde Pierce. She's a doctor of pediatrics. And they wanted to go, they had this as a 2D, but they wanted to go to 3D and want to collaborate with us to develop this application. They have over 1,800 children die from abuse and neglect. 70% of the children who die are 3 years or younger. And so this application, and 9 times more likely to commit crimes if they're abused. And so this application was based on data from 2,100 patients. A third-party developer actually developed it using our mobile SDKs for iOS and Android. And here's just a picture. And so this is an integrated view with our Plasma engine. And you can see as you start, you select male or female, and it's essentially a body map, a custom view of body maps. And as you select the different parts of the skin, you select your model, the different parts of the skin, it's loading on demand, as with many of our applications, and it gives you the plausibility of if that child has been abused or if it's an accident. The next application is the SmileTrain Virtual Surgery Simulator. SmileTrain is one of the biggest charities, surgical charities in the world. It augments the current doctor's training using our WebGL engine. And it's a sustainable and robust training platform that's available to all surgeons free of cost. They recently did a 12-year study, and it shows that this is very powerful. It's so easy to distribute. It's so cheap to distribute. And that's why it's one of the great ways it's in 3D. We have 12,000 active users in 148 countries. Here's a view of just a very quick view of that SmileTrain engine. As
critical to the surgical management,
you can see here,
lateral cleft lip deformity.
you can go between the normal and the cleft state, and people are learning how to do hardcore surgeries. Doing this, I'm not showing any surgeries here. I'm just showing the deformity. But there are 24 modules, I believe, in this system that's custom for that SmileTrain training, and it has a very large impact. Increases knowledge and confidence for local surgeons who are our target in developing countries. Available in 5 languages. And SmileTrain has performed over 1.5 million surgeries and used this technology as one of its main training tools for the last 10 years. And then finally, I just want to jump into some of our XR implementations. And this is a little bit off the beaten path, but this is our Google BioDigital partnership that we started in May of 2020 when COVID hit. And it's, our models are, Google is looking for a partner to kind of teach STEM when all the schools shut down. And we integrated this into search with Google, but it actually doesn't use BioDigital. It uses Google's scene viewer. So if you were to go on Google, skeletal system, you would get, I think, like halfway down your view, you'd see 3D models. It takes a little bit to scroll down, but it's integrated into the actual search. And if you click on it, it will work in augmented reality on a mobile device. And I think I don't know exactly how many views it has, but it's a pretty ubiquitous, large implementation. So any of the systems we have, skeletal system, muscle system, they're reduced and optimized, but they work great in Google Scene Viewer. And lastly is our, the final implementation I'll talk about is ZSpace. We partnered with ZSpace for their high school education program, and it's a lenticular display without 3D glasses. We're using our WebXR. This is our newest implementation using the Plasma engine on WebXR, and you can scale, you can move that anatomy around and use their stylus. And this is more for high school education. All right. And that is my last slide.
Excellent. Thank you so much. That's very powerful. Next up, we have Oleksandr Popov. Oleksandr, if you want to take over the screen.
Okay, you should be able to see it.
Looks great.
Yeah, hello. So I'm Oleksandr Popov, and I live and work in Kyiv, Ukraine. And today I will showcase some rendering techniques used in my latest WebGL demo, Stylized Castle. This WebGL demo has stylized art direction, has simple shapes, mostly untextured. It is implemented with a custom low-level WebGL framework, which is not a ready-to-use engine. This framework has API identical to the same Java Android framework, and which is used to create the live wallpaper application. Size of this demo is quite large compared to the previous ones. It is 2.2 megabytes of uncompressed data. This is because of quite high poly count, 95,000 of triangles. The reason of such high poly count is that as an editor for the scene, an AssetForge app was used. And this is a Kitbashian editor, which exports scene as these really large combined meshes. And the demo doesn't use instance rendering here yet. It just renders these exported geometries as is. Good candidates for instance rendering would be, of course, trees and cannons and other duplicated geometries. So what objects is this scene made of? These are static geometries and animated objects, knights, eagles, flags, and wind stripes. To add more depth to the scene, simple fog and shadow maps are used. So first, let's take a look at static geometries. To reduce size, compact data types are used for vertex data. Total vertex data stride size is just 12 bytes. Vertex position is stored in three half precision floats. Three normalized signed bytes are just enough to store normals, and the color is just a single byte because shaders use indexed colors. To add more depth and detail to the scene, shadow maps are used. These are simple single cascade shadow maps with a resolution of 2000 by 2000 pixels, and for soft edges, the combination of both hardware linear filtering and 5-tap PCF is used. And PCF stands for percentage closer filtering. It is basically just sampling of some nearby pixels and calculating the average color of them. So here's a comparison of different shadow filtering implementations. First one is no PCF. It is completely unfiltered. Second is PCF of 5 taps, and the last one is 9-tap PCF. And here's the same filtering, but with hardware filtered shadow texture. And as you can see, it significantly improves image quality. And as you can see, there are virtually no difference between 5 and 9-tap filtering. So according to the golden rule of real-time graphics, this looks good enough, and the 5-tap one is used. To avoid the shadow acne, two biases are applied. The first, in vertex shader, a small bias is applied to slightly offset geometry in light direction, and in fragment shader, a bias of 1.5 pixels is applied before sampling shadow map. Both values are hand-picked, but can be adjusted. To improve performance of shadows, a couple of tricks are used. First is a really simple one. Just update shadows at half frame rate. This is quite often used in the console games, and it is virtually unnoticeable by end users, especially on the high refresh rate screens. The second one is to apply PCF filtering only for fragments closer to the camera, and don't use PCF far away. This, of course, adds a branch into the fragment shader, which is typically considered as a bad thing. but it noticeably reduces memory bandwidth, which is especially important for mobile devices. For example, on my Pixel 7a, this reduced texture unit utilization by approximately 25%. To render objects to the depth texture, the special depth-only shaders are used. Since these shaders don't need to provide any color output, their fragment shaders are completely empty. And yes, this is a perfectly valid GLSL fragment shader, not a typical one. The typical shader output is color, which is what you see on screen, and depth, which is written to depth buffer and is used only to cull fragments. However, these shaders don't provide any color output and are used only to render scene depth information from light source point of view. As you can see, shadows add more depth to the scene. Without shadows, it is quite hard to tell if the trees are floating midair or are actually grounded. And also, scene becomes more alive and dynamic because moving objects, like for example birds, can cast shadows even they are out of view. The most interesting objects are animated ones. So all of them are animated procedurally. No any baked skeletal or vertex animations are used. And the simplicity of these objects allow them to be animated in vertex shaders relatively easily. First, let's take a look at the animated night characters. The model of this night is very low poly, which makes it easier to animate procedurally. Nights are animated in shader to reduce draw calls, otherwise it will be 4 separate draw calls for each body part to animate it. Another benefits of procedural animation approach are that it uses more compact vertex data and provides better control over animation compared to the baked solutions. So to animate night, vertex shader must somehow detect a body part of a current vertex. And vertex data has only positions, normals, and texture coordinates. No additional information like bone ID or something else is present. Positions and UVs of different parts can overlap. For example, bottom of the head is the same as top of the body, which means that we cannot rely on positions on UVs of these vertices. So to split model into separate parts, vertex data is just grouped into sections for each separate body part. First is body, then next is head, and then arms. Animation is then controlled by 3 rotations past one uniform. Here's an example of shader code. It uses GL vertex ID to detect different body parts. Because of model's simplicity, it doesn't have separate legs. So for better working animation, a simple bobbin is added. This bobbin is just an absolute value of sine wave, which creates a rather convincing illusion of working. Eagles are animated with a very similar shader, but it takes only a single rotation uniform because there are less moving parts. Another animated objects here are flags. Animation is inspired by the fish animation in the game Abzu. The simple sine wave is applied to vertices while reducing its amplitude closer to flagpole. To correctly apply lighting, normals are also bent. To bend them, the cosine wave of the same frequency is used since it is derivative of sine. Wind stripes. Wind stripes are inspired by the wind effect in the Sea of Thieves games, however, in this scene they are more curly. This one is even more procedural than the other ones because it doesn't use geometry buffers at all, and it generates all triangles based on vertex ID. So how does it work? Let's take a look. For example, we need to draw a wind stripe of 20 seconds. To do this, all is needed is to issue GL arrays call with 20 times 3 times 2 triangles. And no buffers with any vertex data are bound. In fact, vertex shader doesn't even have attributes. This is again not quite typical usage of OpenGL shaders, but yet a perfectly valid one. So let's take a look at this short 20 segments wind stripe with some test coloring of segments to clearly visualize geometry. Vertex shader generates vertex positions based on GL vertex ID. Both ends are tapered with a simple smooth step. Then a distortion in XY plane is applied, and distortion in Z direction is applied. Here's a final result without test coloring. And here's how all objects are combined in a scene. The base of scene is a simple ground plane with fog. Then batched static geometry is added in 2 draw calls. Animated objects are added. And here's the final look of the scene with shadows. Thank you for watching. You can find links to live demo page. It's source code on GitHub. You can get Android wallpaper app on Google Play. More information can be found in my article on Medium, and I have to give credits to author of original 3D assets and models and asset forge editor, it's Kari. And yeah, that's all from me.
Thanks, Oleksandr. That's pretty neat. Next up, we have Kari Lavikka, and we'll demonstrate GenomeSpy. Kari, go ahead and take over the screen.
All right. So yeah, I'm Kari Lavikka, and my presentation is about GenomeSpy, a visualization toolkit for genomic data. So I'm a PhD student in Hautaniemen lab at the University of Helsinki. I'm doing cancer research, but I'm actually focusing mostly on biological data visualization and tumor evolution and bioinformatics. And I have one slide about biology. So human genome comprises 23 chromosome pairs, and these contain over 3 billion base pairs of information. But particularly in cancer, the genome gains mutations like point mutations that change these base pairs, or chromosomal mutations that alter the structure of the chromosomes. But these are quite different when it comes to their scale. So this kind of multi-scale data that has to be visualized at multiple zoom levels. And at this point, I have a couple of demos. Just a second, I'll share them. Yeah. So these are based on GenomeSpy. This is a tool that allows the assessment of automatic data analysis. So on the x-axis, there are chromosomes like chromosome 1, 2, 3, and so on. And this shows copy number data, meaning that if some parts of the genome have been multiplied or deleted. In a normal genome, you should see just a single horizontal line here, but apparently in this particular case, there are some aberrations like amplifications and deletions, meaning that some DNA content is missing. But anyway, this tool is interactive, so the user can zoom in and out and this is supposed to look super smooth at 60 frames per second. But anyway, these blue points in this scatter plot show a kind of raw data, and these black lines show automatic segmentation. So now the user can assess whether this segmentation makes sense. So for instance, here it looks good, but on the other hand, at some places, maybe this segmentation didn't quite work. Then let me show another example. Okay, yeah. So this visualization is mainly for data exploration. Now we see multiple biological samples here. And the geneticists in our lab are using this a lot to just explore the genomic data of the large cohort we have. Actually, this has about 800 samples. Let's filter this a bit. Only keep the better quality samples. Anyway, you probably can already see some patterns in this data because specific parts of the genomes are altered in certain cancers. And again, these genomic axes can be zoomed in, but if you happen to see some interesting outliers here, then you can also peek these individuals' samples easily. Yeah, so data exploration is important, especially with genomic data, because statistical methods alone cannot catch all these interesting features that a user might find by just looking at this data set. For example, here are a few samples with a specific pattern that looks quite different if compared to these other samples, for instance, and so on. And because of GPU use, this tool is able to show huge amounts of data that can be easily easily navigated and explored and zoomed in, out, and so on. But now let's go back to my slides. So then what is GenomeSpy actually? It's a visualization toolkit. So you may have a novel visualization design idea and some data. Now GenomeSpy provides you with certain building blocks that you can put together into a visualization specification. And then GenomeSpy renders these custom visualizations using GPU accelerated graphics. However, this is heavily inspired by WebGL. So visualizations are composed from marks like rectangles, rules, points, text, and so on, pretty basic blocks. And each datum in your data maps to a single mark instance that can be controlled using visual channels like position and color and so on. But also between the raw data and these channels, there are scale functions. And then you can use view composition to build complex visualizations from multiple different mark types, like layering and concatenation and so on. So here's an example of a single simple visualization showing a nucleotide sequence, and here's a specification. So here we specify some data that is loaded dynamically. Then we define how these visual channels should be used, so which fields should be mapped to the channels, and then we use layering to superimpose these colorful rectangles and these letters. Then not this one. So on the GenomeSpy website, there are multiple examples of visualization. I'll show you one. So this is a playground application. So the specification is visible here, and I could edit this, and then the visualization would change. So this visualization shows the so-called GZ content across the whole genome. There's plenty of data, but once I zoom in, then more detailed data are loaded, and also these scale domains are changed, so these axes and colors adapt to the data. And then just a quick example of a different kind of visualization. So now we have also these link marks showing the so-called structural variation in the chromosomes. So let's go back to the slides. So how GenomeSpy uses WebGL. So each mark type has a vertex and fragment shader. And an important feature is that all these scales are implemented in a GLSL. So GenomeSpy stores raw data in vertex buffers, and then the scale functions implemented in GLSL do the mapping from scale domain to range. So it means that, for instance, zooming in and out is just changing the domain using uniforms. So it's super fast and very efficient when it comes to CPU usage. There have been some challenges. The main challenge has been that the precision of 30-bit floating points is not sufficient for these over 3 billion unique genomic positions. And I've been using emulated 64-bit floats, but it has been quite difficult because shader compilers tend to optimize them away. Currently, I'm using this kind of hack, which works now, but I don't know when it breaks again when some new optimizations are implemented in the shader compilers. Then there are some future ideas, like instead of storing data in vertex buffers, I could use textures instead. The multi-throw extension would be nice to have, but GenomeSpy is not that CPU bound at the moment, and Firefox doesn't support it, so I'd rather live without it. So that's about it. Thanks.
Okay, I'll talk about a Moldstar app called Mesoscale Explorer, where we are scaling web molecular graphics to whole cells. And a few words about Moldstar. Or first, my name is Oleksandr Rose, and I'm one of the principal developers of Moldstar. And Moldstar is a largest suite of tools for handling molecular data on the web, but a big part of it is 3D visualization. You can see an example of a small protein structure on the top right of the slide here. And it started as a collaboration between a few scientific institutions in 2017, and we developed it quite openly in GitHub, and it's liberally licensed and widely used in academia and industry. I gave a presentation on the rendering tech in Moldstar last year at this meetup, so if you like, you can have a look there. But today I'd like to talk about scaling in Moldstar. Yeah, what I mean by scaling is here being able to explore molecular models with billions of atoms instead of just millions, such as models of whole cells or significant parts. You can see an example of where we start and where we got on the right. So Moldstar's original goals did not really include rendering such models. And if we try to do it by brute force, a number of bottlenecks became apparent. So one early issue was GPU memory. use, and I was blocking because it would just crash the browser. There's also the amount of work done in shaders was another bottleneck, depending on scene and lighting settings, either in the vertex or fragment shaders. But more generally, issues overdraw and just too much subpixel detail. A pixel would represent more than one atom even. So that's not just costly, but it also introduces aliasing and flickering for no benefit. Luckily, there are plenty of approaches to solve these problems. We started using vertex pulling to get rid of a lot of duplicated data and drastically reduce memory usage, and generally optimized key functions in the shaders and use approximations where possible. I won't go into details on those, but there's an extra slide when I publish this presentation. But the biggest effect on scaling to billions of atoms we got from adding support for level of detail, or LOD, and culling, mainly frustum culling, but we got some benefit from occlusion culling as well. So to do LODs and culling, we need to split and group our instances, the instances of molecules spatially, so we can cull parts of them, show others at different levels of detail. So let's start with some definitions. LOD, or level of detail, means here we want to render objects with different detail based on their distance to the camera. And for culling, we want to decide what we actually need to render, we need to send to the GPU based on some spatial criteria like camera frustum. And lastly, instances. Instances allow us to render the same object at different positions with different rotations. Instances here are our molecules, which are comprised of atoms. Generally, the dilemma we are faced with is the following. The more instances we can process together, the less work the CPU needs to do instructing the GPU what to do, or what to render. But if there are too many instances, the GPU just gets overwhelmed, and even having that many instances does not make visually a difference. So we need to balance the work the CPU and GPU do between deciding of what to render and actually rendering it. As a side note, if the GPU could schedule its own work, we could do both on the GPU, but that's not possible with WebGL, but hopefully it will be with WebGPU. So to do a fully GPU-driven rendering pipeline, that would be cool. So our approach to splitting and grouping of instances is to use a two-level grid, like shown in the top right, just a 2D representation. We first group instances in the bottom level grid with smaller cell size, and then in the top level grid with a larger cell size. And when doing LODs and culling, we first look at the top level and see if we can avoid looking at the bottom level at all. And to draw the instances, we use the WebGL draw instance space vertex space instance extension when available. And if it's not available, we have to issue separate draw calls and call vertex attribute pointer, which can be somewhat expensive. But generally, in our use case, we can get about the same speed if we ensure that spatially close instances can be drawn together as just one range in a draw call. If we can't do that, it's much slower. And then, so we only have one type of geometry in our scene, just spheres. So we thought maybe we can do some bespoke LOD system that's more efficient than something generic. So in a generic system, you would just have separate geometries, for example, for each level, and simply height show them on certain camera distances. But here we process our sphere geometry such that it represents a hierarchy that we can use for all the levels of detail we need. So for the less detailed levels, we would like to replace some number of spheres with a representative sphere that tightly covers the spheres it replaces, like in the example in the top right. Yeah, we do the following to implement this. For the representatives, we reuse existing sphere. We just use the every nth sphere, actually, since proteins are essentially space-filling curves. And then we reorder all the attribute buffers for the spheres so that less detailed levels come first, as shown in the bottom right. And then we can draw different levels by simply using different ranges of the attributes, and also setting and scaling uniform. And this allows us to share almost all GPU resources between the LOD levels and save about half the memory compared to a generic approach. And lastly, we do two types of culling, frustum culling and occlusion culling. Let's briefly look how we do them. With frustum culling, we want to only render what is within the camera frustum and thus potentially visible to the user. And given our two-level instance grid, we first check if top-level cell overlaps with the camera frustum. Then only if it does, we check the bottom-level cells contained within for overlap with the camera frustum. The example in the top right, only top-level cell 3 overlaps, and within it, only bottom-level cells A, C, D overlap. All of the cells and the instances contained within will not be rendered. With occlusion culling, we want to avoid rendering cells that are completely occluded by things actually rendered. So how do we know that something is occluded? Oh, we can render everything and check if any pixel of a cell shows up on screen, but then we wanted to avoid rendering everything in the first place. So what we do is we use what we rendered in the previous frame and then reproject the cell bounding spheres at that point in time. And to that, we use a hierarchical Z buffer that we get asynchronously and calculate on the GPU using the pixel pack buffer available in WebGL 2. But still doing this depth check is expensive, so we only check the bottom level cells when they are close to the camera. And that's also when culling them gives most performance gains. And so let's look at some performance and generally scalability. So one aim was to allow exploration of whole cell models on laptops. We defined 4 presets to trade visual quality for performance. The table on the top left call them ultra quality, balanced, and performance. And in them, we use 4 settings to tweak. And so one is culling. Actually, we always have that on. There's hardly any point disabling frustum culling. But if your CPU is much weaker compared to your GPU, disabling occlusion culling can help with our implementation. And then level of detail is how many levels we have and at what distance we switch between them. In the top right, you can see a difference between high or the quality and balanced setting when fully zoomed out. Now with the balance and performance presets, you'll generally see more pronounced pop in and pop out when zooming. And resolution is how much we downscale from the full display resolution. But since our fragment pixel shaders are comparatively cheap, it doesn't kind of do as much as you may be accustomed to from games, but it still helps. Then approximate sphere imposter rendering, so that's often balanced in the performance preset. In the bottom right, you can see the visual effect on the approximation. It reduces quite some artifacts, but it can also greatly speed up things. So the zoomed out scene can be rendered at 60 frames per second, well, with vsynced on a current generation gaming GPU with any preset. So you may ask, okay, maybe we don't need LODs for this GPU, but if we try it without, it actually takes 400 milliseconds to render it zoomed out and 100 milliseconds zoomed in. And then back to our goal, we wanted to be able to render it on laptop GPUs. So it's one from 2019, and it struggles to do it at the quality setting, but you can get an interactive experience with the balance and the performance preset. Now we can look at some individual settings. So the resolution and occlusion culling give us about a 5 to 10% improvement, and the approximate sphere flag can actually give us a 2x improvement. I think that's mostly because we're not writing to GLFrag depths, which seems to be very expensive on that GPU. Now with that, let's do a quick demo in the other tab. So I loaded up this approximately 2 billion atom model, 2 billion instance atoms and 500,000 instances, and there are, I think, about 200 different molecules in here, so you can move it around. You can zoom in and look at this proteins in detail. So the whole thing is also filled with stuff. You can see, so you can clip it here and look inside. There are lots of detailed structures. And with that, I'll end my presentation, and thank you for listening.
Now we will open the floor for the Q&A portion of the webinar. Please feel free to submit questions to any of today's presentations using the Q&A feature on the Zoom toolbar. I ask now that all the presenters go ahead and turn on your cameras, and I'll hand it over to Ken. Ken?
So hello again. Thanks everybody for awesome presentations, and I apologize for the technical difficulties. I advised everyone to use Zoom in browser, and looks like there's some issues. So I've already sent 2 emails to the Zoom team, and we'll figure out whether those were in the browser or in Zoom. So going over to where is, okay. Well, right now we got no Q&A. So please, folks, feel free to, oh, here we go. Carl Sims. Super. I think I remember you from MIT. Let's see. Here's a question. Should WGL math functions give consistent results across different platforms? And if so, is there a spec that describes the expected behavior for non-obvious cases? So ATAN 2 of 0, -1 gives pi on some platforms and -pi on others, and the POW function gives different results for negative input values. That's a good question. Let me say that the WGL specification and the conformance suite are much more rigorous than most other shading languages, including, say, Vulkan's Spear V-test suite, definitely more rigorous than WebGL. What I would encourage you to do is please, give that test with the boundary case on, say, the matrix chat, and let's see whether or not WGL is trying to tightly define this. Clearly, it's that edge case. But in general, the WGL test suite is exercising, measuring ULPs of precision in various ranges across the domain of all of the built-in functions, and it is generally very, very, very rigorous. Let's see, Kelsey, would you like to follow up at all on this?
We do have, it's totally possible that we've specified it already. It's possible we haven't specified it already. There is a WGL spec. And if you look in the WGL spec and search for example, ATAN 2, you see the example implementation for how it's supposed to work. If that's incomplete or if it's not being implemented properly in browsers, come talk to us, file a bug, and we'll figure it out. We do generally want to try pretty hard in WebGPU to make it so that even invalid inputs to math functions have the same output everywhere. That way, if someone messes something up very subtly, it doesn't cause really weird, hard to find issues. So we're super interested. If you have more examples like this, come talk to us on Matrix or file issues in the bug trackers. You can start with the WGL bug tracker. But anywhere is great. Thanks. Yep.
Sounds good. Thank you. And by the way, Carl, the POW function with -x is also an undefined behavior in the WebGL shading language. And so if that's what you're running into with WGL, that might be why, but we should try to nail that down. We also don't want to slow down all apps, by the way, by doing something like having to take the absolute value of the what is it? The X value of POW, for example. Okay, anyway, going on. Wayne Choi asks, can WebGPU support the execution of precompiled shaders? Kelsey, would you like to talk about this?
Yeah. Precompiled shaders. Not in a way where you'd like, I don't expect that we'll have a way for you to like precompile shaders the way you might be useful on native APIs. What is more likely is that there might be room later down the road for more control from user apps about being able to reuse compiled shaders, store compiled data, stuff like that. We haven't looked into it too much right now. But generally speaking, like you won't be able to like compile on your machine or on your dev server and ship that binary to users. Like I don't expect that to happen. But if there's something about it that we're not getting or something like that, reach out to us. Like even though I'm telling you, like it probably is not gonna happen the way you might expect. File an issue on the WebGPU bug tracker on GitHub, because we will then publicly in a more full form like be able to tell you like what we expect to happen there. But I think the short answer is no.
Thanks, Kelsey. If I can, dive in with one addendum. In the WebGL spec, this was requested a long time ago, and Wayne, it's simply not possible to do if you're thinking about like a binary blob, because the browsers all have to validate the incoming inputs. On the web, inputs are untrusted, and so there must be a way for the browser to take a look and see whether or not that thing looks valid, which is why we didn't specify a binary shader format for WebGL, for example, and one of the reasons why it's more difficult for WebGPU. WebGPU, of course, has a textual shading language, WGSL, and it is imported and compiled by the browser and validated by the browser. Thinking about, though, the notion of precompiled shaders, WebGPU as an API supports pre-validation of your rendering objects in state, where WebGL didn't. So as you're building up your rendering and compute pipelines, the browser is compiling and reusing all of the validation, the pre-validation that occurred for that pipeline object ahead of time, which makes your rendering calls more efficient later. So the API is structured in a way to support more efficient rendering than the WebGL family of APIs, because during draw calls, WebGL has to validate that the entire rendering state is valid, where WebGPU can actually pre-validate all of that. Okay. So right now the Q&A is fully answered. Does anybody else have questions today? Can any of the presenters talk about hiccups that they've run into using either the WebGL or WebGPU APIs recently? Things that we should focus on as browser implementers.
I have a question for BioDigital. For your largest scenes, how many polygons are getting rendered at the same time for the full human body?
Oh, yeah, it's a little under 6 million. A little under 6 million, about 2 million of which are instance.
Do you use instancing in your engine for any of your modules?
Yeah, like our a lot of our vessels could be instance. When we some of the bones, when we have a direct reflection, we use it. So in some of our systems, but not everything. A lot of times you think it's like a direct, you can easily instance it, and you can't. There's always a lot of unique objects that cannot be instanced, unfortunately.
Thank you. And I did, sorry, Ken, I'm not trying to take it over, but I did have one more question I have for GenomeSpy. It seems to have similarities to Vega Lite a grammar of interactive graphics. Where are the most significant differences?
Yeah, of course. So the grammar is pretty much based on WebGL because its design is super good. But WebGL, well, it doesn't support genomic data. It has no knowledge about genomic coordinates or chromosomes or things like that. And another thing is that its performance is just insufficient for, millions of data points. So doing this kind of exploration of large sample collections and trying to find patterns across these samples and things like that, it wouldn't be possible with WebGL visualizations. But of course, WebGL has support for things like geographical data and stuff like that, but they are not useful in a genomic analysis tool. So I've left things like those out. So those are maybe the most important differences.
Super. And Jeff, no worries. Everybody, please, feel free to pitch in on Q&A stuff. We've got a couple new questions that just came in, so why don't we run down those? So Oyvind asks, what is the future for compute shading in the browser? Websites like compute.toys are a nice showcase of this. Kelsey, want to give the first answer?
Sure. I guess the most obvious future for this is that WebGPU has compute shaders, so like the future is bright for compute shading in the browser, I would say. And like there's still iteration there. There's still a bunch of like cool stuff we were expecting to add for compute shading, for compute shaders, to handle a lot more kind of sophisticated and tricky and kind of rocket surgery kind of designs for compute shaders, but it should be getting better day after day.
Yeah.
I have one thing to add about compute shaders. So WebGL at one point had compute shaders, but then they were dropped in favor of WebGPU. Some older builds of Chrome had them maybe under developer flags, but they are not present in WebGL now.
Yeah, that's absolutely correct. The working group thought about this at great length, and there was sort of a limit to what could be done in the OpenGL style of APIs, and continue to evolve that structure while still adding radical new features like compute shaders or ray tracing. WebGPU is designed after the new crop of APIs, patterned after it, and is much more extensible in terms of adding new pipeline state, for example. The ability to federate in compute shaders. Bindless is a definite possibility. Ray tracing is a definite possibility, although the primitives are not really portable right now between APIs, and so it'll be challenging to integrate that feature. But yeah, looking forward, we want to expose the hardware facilities that are present in a portable and safe way. And a lot of good progress has been made. Intel in particular has been helping us integrate primitives useful for machine learning in the browser. And there's a lot of cool stuff you can do with client-side ML inference and even training, all in browser. Just take a look at Hugging Face and Transformers.js, which is now bringing those models onto your GPU via WebGPU. So a lot of cool functionality and applications coming out. So please stay tuned. Anybody else want to comment? Okay.
I have a question to the browser vendors. So when developing my WebGL applications, I would like to do some better performance profiling, and I find it very hard to do that for the GPU side of things. So I wonder if there are any plans to have well, something like the performance tools that are available in Chrome and Firefox, but for the GPU side, where you can really drill into what's happening in the shaders. Or a good
Yeah, unfortunately
support
not
for
on our
external
side.
tools.
Yeah, we kind of expect performance graphics like engineering to happen predominantly with external tools. There's some things we're working on, like the KHI debug extension stuff that we're thinking about to try to make it easier to see like what texture is this when you load it up in like RenderDoc or something like that. But fundamentally, like we think that it would be a huge undertaking for the browser to kind of paper over all the differences between all of the different like GPUs and what they expect and how to tell you about performance information there. Whereas like we encourage you to use the existing like driver vendor tools to dig into that kind of thing. Unfortunately, like I wish we could give you like a about graphics benchmarking thing, but it's pretty difficult and pretty dependent on the like actual GPU you're on, or certainly the actual architecture. That's a great question.
We're also trying to do
Thanks.
better on this in WebGPU than we did in WebGL. There are already some cookbook documents on how to like attach RenderDoc to given browsers like Chrome. You have to, of course, turn off the GPU sandbox because it has to be able to like attach, inject its DLL, and then write files to the disk, which would be totally prohibited for security reasons in normal browser usage. But you can get traces out of apps today, and we're going to be working more on, making this work well for WebGPU. Okay, super good question. Thanks. Let's see. And the next question from Jashuran is, it's exciting to see the progress on WebGPU support. Perhaps I missed this. Do we have any idea when it might be supported on iOS? Well, as has been stated many times before, Apple does not pre-announce any product information. And so as soon as it is ready, I'm sure that they will tell everybody, including us, that it is going out on iOS. But I can tell you one thing, which is the Metal API on which Apple will certainly build its WebGPU implementation has very, very similar functionality between desktop and iOS. So we don't anticipate there being any lag in shipment of WebGPU between macOS and iOS. It'll probably just come out in the same Safari release, and then it'll just be everywhere. So that will be a happy day. And you can watch the WebKit open source repository and see the commits going into the WebGPU subdirectory. And if you need a pointer, ask in the Matrix chat and we can help find it for you. So a lot of work's underway, I'm sure, by the Apple engineers, but there's no pre-announcement. Anybody else want to comment?
Yeah, no, that covers it.
Okay, super. Thanks for the questions. We do have 8 more minutes in case anybody wants to ask more. Any co-presenters want to discuss anything? Oleksandr, is it possible to turn on instancing support in the Asset Forge editor to reduce your binary size?
Oh, no, it just doesn't support anything like that. I have contacted its author to provide a simple headless export, and even that is not possible. It's a simple tool created by one person, and it's just not possible for him to allocate that much time to improve things. But the output not an output, but the actual format of the scene itself in Asset Forge editor itself is a text file, so I can parse it and maybe extract individual objects from it, because it's plain text in some really simple delimited format.
Okay, cool. Yeah, we're hoping that more instancing primitives in WebGL as extensions, the multi-draw extension, and hopefully I'll put together a test case that proves, based on, for example, Oleksandr's and Kari's use cases, that base instance, base vertex support will actually provide a CPU savings. And then we can just get that in. And then hopefully we can cut down those draw calls from like hundreds of thousands to like a couple of hundred and really utilize the GPU better even in WebGL.
Yeah.
Any more questions that attendees have?
I have one question for Kari. Kari, for the interactions in GenomeSpy, they seem mostly related to zooming. Does GenomeSpy support or plan to support any other interactions in the future? Oh, you're on mute. I'm sorry.
Sorry. Yeah. Zooming in and out is of course the most important interaction when it comes to genomic data, because it's multi-scale. You have to see the whole genome and then, point mutations and things like that. But I might also implement certain things that, for instance, WebGL supports. So filtering individual data elements in the shaders. So for instance, choosing how significant mutation should be shown and things like that. And then of course basic interactions like brushing and linking, but our users haven't had need for those so far. But anyway, there are plenty of opportunities to implement interesting interactions using GLSL.
Wonderful. Any other questions, Ken? I want to thank you and all our presenters for wonderful presentations today. We truly appreciate your time and effort in putting together today's meetup. As a reminder, a recording to this presentation along with the slides will be available on the Khronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us and helps us improve these presentations, and please let us know if there are other Khronos-related topics you may be interested in. Thank you for joining us and have a good day.
Thank you.